Hello everyone, this is your IB guide. Today we're going to be looking at the physics data booklet, and this is basically going to be an overview of all the equations that you're going to be using during the course. So what we're going to start off with is a basic outline of how I'm going to study for my upcoming mock exams. As you know, my mock exams are going to be coming up. So first of all, I decided to look at split the course into three, basically three components. And I realized that 50% of the course is based on formulas, pure formulas. And then the other 50% is split in half between concepts and graphs. So this video is going to be based on the 50%, which is concerned with graphs. And then the other 25 and 25% I'll discuss in other videos that should come up soon. So one of my HLs is physics. So today I'm going to be basically looking at the core. I'm going to be looking at everything in the core from chapter 1 to 8. And for chapter 9, for the HL part, I'm just going to be looking at chapters 9 and 10, since they're going to be coming up in the upcoming mock exams. I just really want to study for the mock exam. So starting off, we have these equations. So the area of the circle, circumference, etc. The A stands for the area, C stands for the circumference, and V stands for volume, and R stands for the radius. R is the radius. So these equations are going to be helpful when you solve equations in chapter 6 and 10. You're going to be needing these equations as well as other equations in the other components, such as maybe the volume of a cube, height times width times length, and also you might be asked to find the volume, for example, of a cylinder, and a cylinder is basically a prism, so it's the area times the height, and that will give you the volume. And also the area of a trapezoid. So this is a trapezoid. Sorry, this is a trapezoid. This is one side A. This is the other side B. And this is basically the height. So the formula for the area is equal to half A plus B times the height. And then there are also other equations that you're going to need to know, such as, well, not really equations, but it's kind of a concept, but you could really regard it as an equation. So for example, if x is less than y, we say that x significant figures multiplied by y significant figures. We take the lowest one, so this will give us x significant figures. You always write the final answer with the lowest significant figures. So let's say here we have 2 significant figures times 3 significant figures. We will have to write the final answer in terms of 2 significant figures. And what if we want to add or subtract? This is also the same for division, so this is also division, the same concept. But how about if, let's say A is less than B. Okay. Then we have a decimal point. So in addition to subtraction, we look at the decimal points, plus or minus B decimal point. So the final answer will have to be in terms of A decimal points. So 2 plus or minus, so of course this is decimal points, 3 decimal points, the final answer will have to be in terms of 2 decimal points. And when you're writing uncertainties, and this is what we're going to be moving on to now, when you're writing uncertainties, the uncertainties basically have to be in terms of one significant figure, unless, sorry, one decimal point, unless the number before is 0, then you take the second. So you take 2 significant figures. So that's in terms of uncertainties. So this moves us on to, and these are of course are going to be constants that you're going to be need to use, and conversions as well. I'll discuss these later, and this will be discussed in a later upload with the concepts. So here we have our first set of equations. Y is equal to a plus or minus b. So basically, if you have addition or subtraction, you just add the uncertainties. And if we have division or multiplication, we take the fractional uncertainty. Fractional uncertainty is basically the uncertainty of a over a itself. So we get the fractional uncertainty. You could also add the percentage uncertainty. So for example, if we multiply both sides by 100, okay, times 100, the whole thing here. So you just add the percentage uncertainties. You don't have to do this step. And if we have an exponent, we multiply the exponent by the fractional uncertainty to basically get the answer. Now, there are other formulas. For example, if you're looking at an analog dial or a ruler, you take the lowest measurement and divide it by 2. So let's say the lowest measurement is x plus or minus over 2. So let's assume this is a ruler. So that'll be 0.1. That'll be 0.05. And then in terms of the average, so the average, sorry, the averages. So the average we represent by x with a bar on top. And then this is basically equal to the summation of the number of terms over n. So 1 plus 2 plus 3 over 3, basically. That's what it is. And in terms of the error of the average, we always take the standard deviation. And we don't need to know this equation for the exam. It will never come up. However, this may be useful for your IAs. So summation minus the average squared. And to be honest, you may not need this at all, because you're going to use Excel sheet for your standard to find your standard deviation. So this may not be useful at all. And lastly, to find the error in the gradient, we have this equation. Minus x over 2. And I'll be discussing this with the graphs because it's the gradient of the graph, the error in the gradient of the graph. So this will be discussed later. And this moves us on to vectors. So vectors, we have the horizontal component and the vertical components. So basically, you use SOHCAHTOA. You find these you find the equations for the vertical and horizontal component. So for this one, it's going to be adjacent and hypotenuse, and this will be cosine, and this will be opposites, hypotenuse, this will be sine. And basically can easily derive that using SOHCAHTOA. However, there are other formulas that are not in the data book. For example, how you add vectors. To add vectors, let's say that we have E plus D. We just draw a line like that, and imagine we shift this here. We shift E, and this is going to be E plus E. So tail to tail, head to head. And it's the same thing for subtraction. So let's say we want to subtract e. Okay, we basically move it to the other side like this, and tail to tail, head to head. This is d minus c. And d minus e plus d plus e will give you d. So that's just an extra. And now, how about the magnitude of an magnitude and the angle? So for the magnitude, you basically all you have to do is to find the use Pythagorean theorem. So a squared av squared plus ah squared, and a will be square root. And how about the angle? The angle is basically tan because we have two angles, the opposite. So this is adjacent and this is the opposite. So tan theta is equal to AV over AH. So theta is equal to arc tan AV over AH. So then we're done with topic 1, and this moves us on to topic 2. Topic 2 is mainly based on formulas. So these are your Suvat equations. You could derive these equations. However, I'm not going to do that since it's a waste of time. Instead, I'm going to be looking at projectile motion. So projectile motion, let's say we have y, x. So this is the vertical displacement, horizontal displacement, and this is the motion of a projectile. It's like a cannon. So here we have a velocity that is equal to 0. Sorry, a vertical velocity that's equal to 0 because we still have the x component. And a common question that comes up, especially in paper 1, is that it asks you, for example, to choose the most appropriate answer. And one of them would say that the velocity at the maximum point is equal to 0. This is wrong. It's only the vertical velocity that's equal to 0. And of course, you can use the magnitude formula. Yeah, this one. And you'll find that there's still a velocity. So what we're going to do is we're going to use this formula to derive the first one. So for the first one, there's no acceleration in the horizontal component because we neglect a resistance. So it's just going to be that. And then this is ux. This is uy. This is the displacement. So Vx is equal to u cosine theta. Here it's Vy is equal to u cosine theta. Sorry, uy. We're gonna put minus because in terms of the vertical component we have g. So a is equal to minus g. G, if we look here, is equal to 9.81. So instead of writing 9.81, I'm just going to keep it as G. Since G is not really constant, G on the moon is different than G on Earth. And if I scroll a little bit down, yeah, here. So it may ask you, for example, to derive the G on the moon. So you have, they give you a value for F, they give you the mass, you just have to find G. And of course, this will change. It won't be 9.81 anymore. And so it's going to be U minus GT. and it's because of its attractive nature, it's going to be negative. So Vy u sine theta minus gt. Now we're going to be looking at the x and y displacements. So starting off with x. So starting off with x is equal to, we're going to look at this equation now. So first of all, we have no acceleration so for x, that will be equal to 0. So we don't have to write this whole side. So it's basically equal to ux t. And when we substitute the value for ux, this will give us ut cosine theta. Sorry, times t, or ut cosine theta. And for y, since we have an acceleration, so it's going to be u sine theta, ut sine theta, minus gt squared. Now, what if we want to find the time it takes to reach this maximum point? Well, all you need to do is that you substitute the equation here. So for the Vy is equal to 0. So it's going to be 0 is equal to u sine theta minus gt. gt is equal to u sine theta. T is equal to u sine theta over g. And then what if we want to find the x displacement? Well, we just substitute that here. And we can also substitute it here to find the vertical displacement. So first of all, let's do it for the first one. X is equal to u cosine, so u squared cosine sine theta over g. And for y, it's going to be a little bit longer. Just going to be substituting this. I'm just going to write the final one. So it's just going to take a bit of time. It's going to be half u squared. You just substitute it for t. It's easy. Sine theta over g. And what about if we want to find the maximum distance for the whole trip? You could find this and double it. So it's going to be 2 times this. Or you could say that when y is equal to 0, so you use this formula. So 0 is equal to ut sine theta minus gt squared. So sorry, you just keep this here. This is going to be 0. And then you're going to take a common factor, t. So minus gt. So for one of them, t is going to be equal to 0 because we know that in the beginning, y is equal to 0, and thus t is equal to 0. And now we're interested in the second one, so gt to u sine theta, and t u sine theta over g. Alternatively, what we could have done is just basically multiply this by 2, and we could have gotten the exact same formula. So this is our half. Yeah, so this is going to be 2u sine theta over g. So just multiply this by 2 because it's basically the distance. And then we could find x. As I said previously, you can find x and double it. However, you can also do it this way. Sine theta, substitute this here. 2u squared cosine theta sine theta over g. And then using our knowledge from trigonometry, 2 cosine theta sine theta is equal to, sorry, it's going to be equal to sine 2 theta. So you can just write that instead. So instead of writing 2, just u squared. And then sine 2 theta over g. And that's basically how you derive every single formula for the really every formula you're going to need for projectile motion. Now, what if we had a resistance? So you have to know how the motion is going to be. So this is obviously going to be shorter, and this is also going to be shorter due to a resistance, because it's basically going to be drag force. So we have a formula for this. You may need to memorize part of it for the exam. So F is equal to KV. And this is not derived, this is just given. So you say that mg is equal to kv, because F is equal to mg, and g, sorry, and then v, we're going to find the formula in terms of AV is equal to mg over k. And this is Vt, this is the terminal speed basically is equal to mg over k. So you just memorize this formula. And this is obviously for low speeds. For high speeds, there's another formula, where F is equal to k v squared. K is a constant in this case. And basically, this is going to be square root of that. If we apply this here. So now I'm just going to clear up some space, and we will be looking at the next topic, which is forces. So the first equation that we should know is Newton's second law of motion, which is F is equal to ma, or the summation of forces is equal to ma. So whenever you have an equation, you should use this formula when resolving any equation. You should have this formula in mind. So there are a lot of forces. There are different forces, weight, tension, etc. And each one has its own formula. And it depends obviously on the free body diagram. So this is what I'm going to be showing you right now. So for weight, F is equal to mg. And as we stated previously, g is the acceleration of free fall. So this is W. For W, that's the formula, and we define G to be 9.81 meters second negative 2. Now, what if we want to find tension? So this is basically how you would draw your free body diagram. In the center, this is your weight. Now, tension is different, since you have to resolve a free body diagram. So let's say this is our tension diagram. Okay, this is W, this is T. This is tension, sorry, this is capital T tension. So here tension is equal to mg. Since it's not falling or going up. If it was falling, it was accelerating downwards, we say it's equal to mg minus a. And if it was going up, it's mg plus a. So up is plus and down is minus. So this is going to be the basic concept. And if it's not, it's like detached like this. It's not, it's loose basically. And we have here a component of weight. Tension is equal to 0. So for example, if there's a hand holding it here, there's no tension. It's just a loose string. Now, what if it was held like this? Like, for example, in a pendulum situation. So here we have our W. And here we have a component that is equal to mg. And using SOHCAHTOA or using your basic vector concepts, this is going to be mg sine theta. And basically, you can just look at this. So this is basically the rope. This is basically this line here. And it's going to be mg sine theta. Now, what if it was in another way? What if it was like this? So you have something here holding it, and it's basically falling here. W is equal to mg. So tension, sorry, we're going to have a normal force. We're going to call this R. So it's usually called reaction force. And this is always opposes the surface. So since this is sloped down, it's going to be like that. And this is going to be mg cosine theta. Which means this is also mg cosine theta. And now in terms of tension, it's going to be the same. It's going to be mg sine theta. Just resolve the forces and you should get that. And now we move on to the forces in a string. So we know that so forces on a string are based on Hooke's law. So tension in a string is equal to kx. K is a spring constant, depends on the string. And this is from Hooke's law. And the x is how much it is extended or how much it is compressed. Basically, this is one of the easier formulas, and we also have the normal or reaction force. So the normal or reaction force is R. So let's represent them as body diagrams. So this is W. This is R. R in this case is equal to mg, same as tension. And we have this example. It's going to be the same. For example, here we have this. That this is W. This is going to be mg cosine theta. And now what if we had a circle? So, and we're looking at the outside of the circle, and this is W. So R should equal to mv squared over R. And this we will take later in the circular motion. So this is basically a force that's always directed to this towards the center of the circle. And what if it was the other way around? What if the norm was R here? So R is at the surface. And in this case, no, sorry, this is going to be mg cosine theta. And here it's going to be R is equal to mv squared over R. And this we will basically take in topic 6, I believe, yeah. And drag force is basically any opposite force, and it's going to be similar to friction. Friction is just going to be using these formulas here. So for static friction, it's going to be equal. And for dynamic friction, sorry, it's going to be equal to this. So this is basically constant of static friction. This is going to be the constant of dynamic friction. And to better understand this, we're just going to draw this graph here. So as you apply force, and until it starts moving, there's going to be less force to keep it moving. So this is going to be the dynamic friction, and the static friction is everything leading up to here. Moving on. Newton's first law states that the summation of forces is equal to 0. So the summation of forces in the vertical, let's say mg minus mg, should equal to 0. And also the summation of forces so opposite minus sorry. The last law of motion will be discussed in terms of the concepts. There's no formula for it, so sorry. This is gone. This moves us on to subtopic 2.3. So now, if we continue, this is the formula for work and kinetic energy, potential energy, and if you can realize, this is elastic potential because we have K spring constant times the length of extension, and then this is potential energy, potential gravitational energy because we have delta H, and power is equal to F times V, and we also have the formula for efficiency. So the first concept I would like to explain is the law of conservation of energy. So the change of energy in a system plus the change of energy in that system surrounding that is equal to 0. And the law of conservation of energy also states that the change in energy is called work. So W is equal to the change in energy. And there's also Q, which is the transfer of heat energy. And we'll take this in topic 3 later on. So now what we're concerned with is when W is equal to the change of energy, or work is equal to the change of energy, and we assume that Q is equal to 0. So the first thing we want to do is, how do we get this equation? So we want to understand what they mean by this equation. So this is your object. Here we have the weight component. And if you're pushing it, we apply a force that way. There's this it will travel it will be displaced, and then we have an angle here. And so this gives us the work done. Fs is equal to work is equal to Fs. Cosine theta. And due to the fact that most of the time this angle is 0, so this is just basically a straight line, this is usually f, it's going to be cosine 0. Cosine 0 is 1, so it's just going to be w is equal to fs. And that should be your formula. Now we want to do is derive the formula for ek. How do we find ek? Ekinetic. We can derive this from Newton's second law of motion, F is equal to ma. And then we rearrange this to make it a is equal to F over m. And then we substitute this formula in this pseudo equation. V squared is equal to u squared plus 2as. So this is how we're going to do it. We're going to just basically substitute this here. Two Fs over m is going to be equal to u squared. And then we just multiply the whole thing by half. So minus half u squared. Okay, and then Fs. Now Fs is work, so it's going to be the change of energy here. Kinetic energy. It's going to be half mv squared minus half mu squared. So this is basically the change of energy, initial minus the one that we have obtained. So basically this is the final, the formula for the final minus the formula for the initial, because it's a difference. So basically ek is just basically equal to half mc squared, mv squared, sorry. And that's how we get it. Now, if you want to derive the next formula, or the one on the string, we say that f, we know f is equal to kx. And we're going to use this formula, w, because it's obviously going to be in a straight line, and the angle is going to be 0. So E potential, or E elastic, let's say. Okay, it's going to be equal to, this is f kx, and s is going to be x times x. It's going to be giving us kx squared. However, here there's a half kx squared, and the way that we obtain this is from the graph. I'll be explaining this tomorrow, or sorry, in the next upload. So when it comes out, hopefully tomorrow. And so you have half kx squared, and the half is basically from the formula, from the graph you obtained it. I mean, I can basically explain it now. So It's more convenient. This is F, this is S. And you know how always when you have a triangle, it's gonna be half the base times the height, so half Fs. This is what we mean. And lastly, we're going to derive the work done by gravity. So I'm just going to write here. There's a downward force. So W is equal to mg. This is the force, and S is the displacement. So, and S is going to be equal to h because we're looking at height. So W, and this is going to be cosine 0 because there's no angle, basically, because h is in the same angles as a force. So mg h, and that's basically the equation for the potential energy. Okay, now we want to find the formula for power. So basically power, we say power is equal to FV. So this is the given formula. We want to find another formula. We want to find the formula for power in terms of work. So P delta S over delta T. So display changing the displacement over time. And then that will be Fs. So the change in work over the change in time. And this is a useful formula. So you have to keep this in mind because it's on the data booklet. And finally, you have your two efficiency formula. You just apply it and multiply each one by 100 and write it in terms of a percentage. Next, we move on to topic 2.4, which is momentum and impulse. So fundamentally, this is the formula for momentum. And this is the formula for the force created and the momentum. And there's actually a way to derive that. Yes, F is equal to ma. And then if you rearrange this, m is equal to p over v. Uh, we actually write acceleration, sorry. M is equal to delta v over delta t. Mv is equal to the change, because we have this change in momentum. Change of momentum is impulse, so that should be known. And then that is over time. There's also another formula for kinetic energy. We can derive that as well. So EK half mv squared. V is equal to P over M. So here's where we substitute that, okay? Squared, we have P over M, which is equal to half P squared over m. And that's basically this. The two goes down. Okay, now we have to discuss the idea and concept of the conservation of momentum, because this formula is basically this formula up here. They're the same. They're equivalent. So the conservation of momentum, if it's elastic means that they collide or one of them collides with the other, and then they move in the same direction. This is elastic. Wait, sorry. They collide and then each one goes their own way. This is the other one is called inelastic. I'm sorry. So basically, for this one, the mass of zero. So this is number one. This is number two. This is number one. This is number two. So for the first one, you want to find the mass and the velocity. So basically, add the momentum before. This is before. Plus the one for the other object. Before, and the equal to 1v1. This is after plus m1v1 after. Sorry, m2v2 after. So this is basically means that the momentum is conserved. P is conserved. It's the same. However, momentum is only conserved in elastic. Sorry, it's conserved in everything except for so it's conserved in everything. However, what's not conserved in everything is the kinetic energy. So the kinetic energy is only conserved in elastic collision. In elastic and perfectly inelastic collision, it transforms into other forms of energy, such as thermal or other forms of energy. So, or potential energy, basically, yeah. So before I write the formula for that, I'm just gonna write. So this is basically for inelastic and elastic. This is the formula you're gonna use, and then m1v1, m2v2. So in elastic, basically they stick together and they become one mass, and then they move in the same direction. So I have one mass here, second mass here. So then as this moves, they just get stuck. 1, 2, and they move in the same direction. So it's m1, it's m2. And then they will have the same velocity. So it's v. Let me just change the color so that you don't get confused. Okay. And now for the second concept we're looking at in terms of energy. So for energy, EK before should be equal to EK after. Only for elastic. Only for elastic, yeah. For an inelastic and perfectly inelastic, you're gonna use something else. So basically here, all you have to do is write half mv squared for the first one, half mv squared for the second one is equal to half mv squared for the first plus half mv squared for the second, and they should be equal. That's how you prove it, basically. For the second one, however, you're going to find EK before separately. You find that number. So let's say that's X. And EK after. So EK after is basically going to be, let's say, Y. And you're going to find out that X is not equal to Y. And then you say QED, and that's how you prove it. And as I explained previously, the reason why it's not conserved is because it's turned to thermal or other energy. And most probably you're not going to be asked about that much. So now we move on to the thermal concept. So here's Q. This is basically work done. Work done. So you might be asked, for example, to substitute the formula for work here and then solve for MC delta T. It all depends on the question. But for this, in terms of thermal concepts, this is just the formula. M is the mass, C is the specific heat capacity, and delta T is the change in time. Here M is the mass, and this is the latent heat. Each material has its own latent heat. So when you're solving questions, you just apply these formulas straight away without really thinking. The reason why there are not a lot of, there's not much explanation as there was in topic 2 is because this is mostly a theoretical topic. Okay, moving on to 3.2, modeling gas. So P is equal to F over A. So let's say this is a circle and it's in a internal combustion engine. So there we have our, this has an area, this circle has an area, and we're applying a specific force. However, what if this force was applied on an angle to the normal? So this is theta, and this is area. In this case, it's F over A cosine theta. So you have to keep that in mind just when you're solving. And then this is just the formula for the number of moles. This is Avogadro's constant. Let's see. In terms of this, here we go. You don't have to memorize it at all. It's here. 6.02 times 10 to the power of 23. You just apply that, and yeah, so this is the, when you're finding the number of moles, so this should give you a mole. This is how many moles you have of that thing. So this is like total flow. When you multiply this by this, it should give you this, and vice versa. That's basically how you do that. And now we move on to PV is equal to nRT. So P, pressure, times volume is equal to N, number of moles, times R. R is also a constant. I'll show you right now. R is the gas constant. It has, it's gonna be 8.31 joules, Kelvin minus 1 mole minus 1, -1. So that's that. And then there's also the formula for the combined gas law. So let's say you're given two pressures or two volumes, two pressures, etc. And then you're asked to find one given the other. You just apply this formula, substitute the numbers, and then you just solve. And you just solve. And there's also Boyle's law, Charles' law, and Gay-Lussac's law. However, I'm going to explain this in the next topic because it's mostly dependent upon the graphs. So there will be an explanation using the graphs. Okay, and this moves us on to the last formula. However, before we do that, I'm just going to derive this real quick from this equation to show you how it's applicable. So basically, if you have this, this will give you a constant. So PV over T is equal to a constant. Okay, constant. So this constant, it depends on the number of moles. So you multiply that by the number of moles. And this constant is R. We call this constant R. So PV is equal to N R. And we bring the T to the other side. That's basically how you derive this equation. And now in terms of Boltzmann equation. So this can also be derived from this equation. So I'm just going to do it here quickly. PV is equal to nRT. And so the pressure is equal to 1/3 rho C squared. And this is basically what Boltzmann defined at nRT. And rho is basically the density. So the density is equal to m mass over volume so volume and volume will cancel. And also here m is equal to n times m. The mass is equal to more mass times m. Sorry, this is capital M. So 1/3 is equal to n m. MC squared, and that will be equal to, here we find n to be n over na RT, and n goes with n R3. And then we have squared over NAT. So now we want this to be half MC C squared, because we want in terms of kinetic energy. So we just multiply this whole thing by 3/2. So that'll be 1/2 MC squared. In other words, the kinetic energy. And this side will be 3/2. Okay. R over NA T. So if we bring this here, R over NA is defined to be kV, or the Boltzmann constant. So here we have EK. This is going to be EK is equal to 3/2 the Boltzmann constant. And T. And although you could basically find the Boltzmann constant using R and NA, they already give it to you, so you don't need to worry about this. It's right here. So that's it. So no need to worry about that. And that's basically everything chapter 3 related. And this brings us on to the next chapter, chapter 4. So in terms of wave characteristics, there are a lot of more concepts that are going to be applied as we move forward. Of course, in the beginning, mostly concept applying. So T is equal to 1/f, and this will be explained using the graph. Here F is equal to MA. Which is equal to negative kx. A is equal to minus kx over A. Over M, sorry. And here it can be seen that A is inversely proportional to X. In addition, ET, or the total energy, is going to be equal to EP. plus ek, which is equal to ek slash ep at the maximum point. So if you draw a graph, it's gonna be just a straight line. That's ET. Okay, and this moves us on to traveling waves. So basically, this is a wavelength. And using the previous formula, we are just gonna divide that. So we know that speed is equal to distance over time. So in this case, that'll be t. And f, sorry, the distance is the wavelength, of course. And that's basically our formula. And if we substitute this, it's going to be that'll be that. However, in this equation, it says c is equal to f lambda. The reason why they put c is because it's the speed of light, and the speed of light is given also here. You don't have to memorize it. So up till now, we have a lot of these constants we know, so that's good. Okay, and this moves us on to topic 3. So I is inversely proportional to this. I is proportional to a squared. I is proportional to x to the power minus 2, and I is equal to that. So starting off top, we know that I is equal to the power incident on an area in this case. A is not the area, A is the amplitude. So I p over 4 pi x squared, and x squared is the radius, of course, the area, or the radius of the sphere, as a matter of fact. And then this is how we prove that. And also the will be proportional to squared the amplitude. This is pretty much given because there's not a specific way to actually prove this. Okay, and then also we learned about polarization and polar lenses in this chapter. So I'm just going to explain the basic concept. You have polar lens, so if only you transmit this. So let's say we have that, the vertical and horizontal components. So basically the horizontal component will not be transmitted, and this will be transmitted. The vertical component will be transmitted. So let's say this, we have that. We have an angle here. Okay, an angle of theta, sorry, an angle of theta. And this is the energy that will be going to the other side. Basically, you're gonna see what is the intensity of light that's going to be transmitted to the other side. So using the vectors, you're going to establish that E, the energy that was going to be transmitted, is going to be that cosine theta. And also, you need to know that I is equal to K e squared. So keeping that in mind, we're gonna write I. So we're gonna write in terms of I. So I is equal to K times E. This squared, okay. And then this will be now if we combine this in a bracket, uh, isn't this basically that? So this is gonna be I naught cosine squared theta. And that's basically how we derive it. And the reason why I derive this is basically show you the concept, the formulas. This you have to memorize, of course. It's not different. So I is equal to K squared minus 2. Or you can actually memorize it from here. It's pretty straightforward. And this moves us on to the second last concept in terms of waves. So now we're looking at wave behaviors. So the formula here that's given is is Snell's law. So let's say we have this is N2, this is N1. We always draw that. This is incident, something is reflected, and something is diffracted along this normal line. So this is pretty much given. However, we can derive another formula for this in terms of the refractive index of a glass cell. This is 1 sine 2. That'll give us the refractive index of the glass. So in case there's a question that asked about that, you know how to find it. Or you can do it the other way around. So you can have 2 over 1, or it has to be 1 over that. And it's basically the reciprocal of that. Okay, and now we're going to derive this formula. Let's take an example. So we have 2 slits here. Let's draw a triangle like that. So this is projected into point P, and this is A, C, and this is O. This is the slit separation S. This is D, distance from the wall or surface. And yeah, this is going to be P. So we want to see the we want to make a formula that will basically represent this diagram. So using our knowledge, BO over CO will give us A1P to this point. So this is C. This is A2. This is A1. Yeah, so A1 is basically that, and then A2 is the second slit. A2 because basically the ratio between the 2 sides of the triangle. This is what we are talking about. Okay, so what is BO? BO is S. CO is D. That will be equal to AT sorry, A1P, A1P, that's the wavelength, and then A1 over times A2, that would be the small. Over D. Okay, that's basically the formula. Check. And next topic that we're going to discuss is constructive and destructive interference. So assume you have two slits. We have a projection here. So these are the wave fronts. So at some point, so basically in these lines where they meet, there's constructive interference. So in these lines, in this line, for example, n is equal to 0. So of course there's another intercept here. So if you draw a line like that, it's n equal to 1. And then there is the midpoint of the intercept between each intersection. And this also creates a line. So this is n is equal to half, and so on. So basically, for the constructive interference, the path difference is this, and for the destructive interference is this. That's the basic concept. Now there's topic 4.5 standing waves, and the reason why the formulas aren't here is because it's basically an external concept that I'm going to be covering right now. So here's an empty page. So let's say we have the first harmonic, n is equal to 1, n is equal to 2. Okay. So this is standing waves on a string or in a pipe that's closed on both ends. So this is one loop. This is two harmonics. I'm sorry, this but the drawing is a bit bad. Just like that. The fourth harmonic. So basically in the first one, the wavelength, we said that this is a one wavelength. And standing waves basically they have it's when they have a path difference of pi, and so they interfere like that. So this is equal to 2L. So here it's equal to 2L over 2. 2L over 3 and 2L over 4. So here's just equal to 2L. Here it's equal to L. And here it's equal to 2 over 3L. And here it is equal to L over 2. The reason why I showed it this way is because we can now establish a general rule. So the wavelength is basically equal to 2L over n. And n is the harmonic. So for the first harmonic, it's this, the second harmonic, etc. Now, how about the formula of f? Okay, we know that using the formula booklet, we were able to establish the relationship between f and v. So subtopic 4. Here, c is equal to, so this is just v is equal to lambda, okay. And we just substitute the value for lambda, and we'll get the, so we'll get if we rearrange this f, is going to be V over that. And so essentially, if we want to substitute this formula here, F is equal to V over 2L, and then V times N. And that's basically the formula. So if we substitute it here, for example, the first harmonic is going to be V over 2L. And here it's going to be 2 V over 2L or just V over L, and etc. So that's how you do it. Now, what if we have a similar scenario where it's open on both ends? It's a pipe that's open on both ends. Open in both ends. Okay, in this case, this is how we draw that. So this is the first harmonic. Notice that here we have one loop. Basically, if we bring this to this side, it's just like that. And the same concept here, just like that. Sorry, this is so 4 is just like that. Sorry, not this. Okay. And basically here we have the same formulas for this. So we basically use the same formulas for here. Exactly the same, nothing has changed. But here we have, so this is basically called the knot. This is the anti-knot, so it's open. And here, basically they're switched. So here we have the anti-knot, here we have the knot. So basically they're the other way around. That's the only difference. Okay, now let's consider a pipe with one open end and one closed end, or alternatively, a string that is loose on the other end. So drawing this here, we have n is equal to 1, the first harmonic, n is equal to 3. I'm going to explain why we put 3 here, and n is equal to 5. So the first harmonic is basically this. Looks like that. And the second harmonic is this. Notice that in the open end, it's there's an anti-knot, so that's why it's 3 and not like the other one. So, and then for 5, it's basically 2.5 loops around that, yeah. And this is half a loop. So here, in order to have one full wavelength, this only goes up like this. It still has to go down and up. So it's only a quarter. So here it's equal to 4L. And here, 4L over 3. Here, it's going to be 4L over 5. And basically now you get the basic formula that will tie the relationship here. 4L over n, where n is a odd number, always. Okay. Now, how about f? F is equal to n v over 4L. So it's basically just 4 instead of the 2, and it's basically everything else is basically the same. So this is basically standing waves, the basic concept of standing waves. And this is basically chapter 4 complete. So now we move on to electricity and magnetism. So chapter 5. Okay, here we have chapter 5. So the first formula here we have is current is equal to the change in charge over the change in time. F is equal to K, Q1, Q2 over R squared. K is equal to 1 over 4 pi. So basically this is the K constant here. And then this is also a constant that we'll have to calculate. So they don't, basically here, they give you the column constant, and the permittivity of the free space formula. So we still have 1, 2, 3, 5, 6, 7, 8, 9, 10, 11. So I'm just going to cross out this because we're not going to use it now. It's part of quantum mechanics, which I still haven't explained, or I won't be discussing it in this upload, maybe another one. And that's basically it. Yeah. So going back, topic 5. That's that. V is the here it's in terms of the potential difference actually, or the voltage is equal to the work over the over unit charge, and energy is equal to force over unit charge, and I is equal to this. I'm just going to explain this later on. So first of all, E, energy. What other formula can we establish from the given information? We can substitute this K, Q. Another way to write it is basically Q, capital Q, which is Q1, and lowercase q, which is Q2, over R squared. And all of that will be over Q. So we're looking at this formula. So Q canceled, E, K, Q, R squared. And that's basically a useful formula for E that you might need. And then we want to find this formula. So first by changing the charge, changing time. Okay. So if you draw this basic diagram, this is A. So the charge is moving this way. S is equal to Vt. So basically the charge, you're going to multiply the mass by the mass times distance. So N A Q delta NK T over delta T. Delta T with delta T cancels. And we're left with an AQ V. This is a V. Okay, and then there's also the electron volt. So 1 electron volt is equal to 1.6 times 10 to the power negative 19. So you just substitute it in here instead. This is the electron volt. So if you go up here, you should find the elementary charge, or E. This is another way of saying the electron volt, and it's in Coulomb. So that's basically that. Now the heating effects of electric currents. Here we are going to introduce Kirchhoff's law, circuit law. So basically, when you have a loop, let me draw a better one. So a loop usually consists of a cell. And let's place a resistor. let's say the current goes from this way. Okay, so you basically draw a loop any way you want. And then, so in this loop, the summation of all the voltage is equal to 0. And at the specific junction, so let's say we have this junction, whatever goes in minus whatever goes out. So whatever goes in is going to be positive, whatever goes out is going to be negative. So usually this is when we deal with double loops like this. So whatever goes in and out should sum up to 0. And then we also have we have Ohm's law. Ohm's law basically states that R is equal to V over I. This is a standard equation. And we can also derive power. So we said power is equal to VI, basically. And we can derive other formulas. So in terms of R squared, that's V squared over R. These are the formulas of power, and they are here. Consequently, they're here. So this is the formula for the total resistance in a series circuit. So if you have, for example, two resistors, and we have a cell here, the way that you're going to find the total resistance, just add these two. And the way we do it in parallel, so if this is in parallel, let's cancel this. So this is parallel. It's going to be 1 over R. So this formula is to be used. There's also a certain way that we know this for a fact. It is basically by saying V is equal to I. R. So we know that in series, the current is constant throughout the circuit. So we do that. And due to the fact that current is just the total is just the sum of all of them. However, in a series circuit, sorry, no, parallel circuit, this is different because the current in is equal to the current out, and the voltage in this case is constant. So we write this equation in terms of I is equal to V over R. So it's going to be 1 over R. As you can see here, it's 1 over R. So the summation of 1 over R, and here it's 1 over R as well. So then we use this formula. Okay, how about the resistivity? So this is the resistivity of a material. It's dependent on the resistance times A times L. So let's say we have specific material A, the length of it is L. And of course, the resistivity depends on the material itself. And from this formula, it can be seen that the higher the length, the larger the resistivity, and the higher the area, the higher the resistivity. And sorry, the higher the length, the lower the resistivity. And it's also worth to mention that usually if you have a voltmeter, an ideal voltmeter, the resistance in it, since we're talking about resistance here, the ideal resistance is infinity. And in an ammeter, an ideal ammeter is equal to 0. The reason being is because ammeters are connected in series, and the current needs to pass through it, basically. And then when we're using a voltmeter, we have to do it in parallel. So when we connect it in parallel to, for example, a bulb or something, it might not detect this from the current. It might not connect the voltage, manage to collect the voltage, because the voltage is not going to be the same, basically. if we connect it, because in parallel, the same voltage goes in and goes out, as we mentioned here. So it's kind of the same concept. So I just wanted to explain that. Okay, and then the next, here we have this equation. We can basically just expand it. IR is equal to V plus IR. And maybe if you want to find, if you give you the EMF and you want to find voltage, for example, you can just rearrange this equation and find that. Okay, and then here we have magnetic effects of electrical circuits. So basically here you're going to be depend on the left and right hand rule, which I'll explain later in the next two uploads. So basically we have this equation for a moving charge, and this equation is for a current carrying wire. So in terms of the wire, we basically have the length and a certain moving charge. So this is of course charge. Okay, for example, let's say that they said that an electron. So we use the elementary charge, which is 1.6 times 10 to the power negative 19 coulomb. So that's how you know how to do that. And since so let's say that sine 90, for example. Okay, that'll be QV is equal to mv squared. So here we're talking about what I'm explaining is electric fields. So if you have an electric field, okay, an electric field is circular. So you just rearrange that m, the v's cancel, mv qv. Then t the period is equal to 2 pi r, the circumference. Time is equal to the circuit, so the distance basically over v, and yeah, that's basically the displacement over that, and we just substitute that for r, 2 pi and v over qb. Q with q cancels, sorry, v and v cancels, so we're left with 2 pi m qb, and this will be helpful finding the time it takes basically. And speaking of circular motion, this is exactly what we're going to take right now. So circular motion is basically the velocity is this way, and then there's a centripetal force. This is the basic concept. So we always know that v is equal to s over r, the circumference 2 pi r over t over r, 2 pi over t. Sorry, this is omega. Omega is equal to 2 pi over t. Then we also have v is equal to 2 pi r over t, and 1 over t is equal to f. So pi r f, which is basically just omega over t. We can also derive the acceleration formula using f is equal to ma and f is equal to mv squared over r. So we basically discussed this formula. If you want to derive this. That's basically how you do that, and we can derive it as well from, let's just substitute the r and then you'll get squared, and then the r's will cancel. So that's basically how you do it. However, there are certain concepts that are not here. So let's say we have horizontally drift. This is one example of drifting, for example. In terms of y, fc is equal to fg. We have fg, fn, and we have a force like that horizontally. So y is just equal to fc or fn, yeah, it's equal to mg in terms of y. And then if you want to x, summation of fc is equal to friction mv squared over r is going to be equal to omega fn mg. So this is sorry, this is n. So it's going to be mg. So next, what you want to do is go on and cancel the two m's. B squared. B squared is equal to, so let's say that this one is equal to mu g. Of course, this is either static or forgot, static or, anyways, it's friction, the coefficient of friction, and gr. So that's that. And how about if we have vertical? So for vertical, let's say you're riding a roller coaster or a Ferris wheel. So 3 positions basically. Okay. Here, Fg. Here we have F and 2 different forces. Here we have it as the same force. Here we only have Fg, and then we have Fc. So starting, let's do the bottom first. Bottom. Okay. For the bottom one, it's we say that the sum of Fc is equal to m squared over r. The sum is basically Fn plus Fg. We know it's equal to 0, but we want to derive this. And so n v squared over r plus. So here it's, sorry, this is a minus because it's opposite Fn. They're going to be opposite way, so that's how we do it. And if you want to further expand this and take m as a common factor, v squared over r plus g. Okay, and then if you want to do it from the top is basically Fn is equal to mv squared. Because it's basically directed towards the center, so centripetal force. So, and we know that it's opposite the surface. So this is Fn. And lastly, from the top, so this is sorry, this is the side. So from the top, it's going to be summation of C. And due to the fact that both Fg and Fn are in the same direction, it's going to be squared over r. We just add them. Minus g. Okay, then if we move on to this side, Newton's law of gravitation. So as we discussed, oh sorry, I forgot one more concept. The last concept is banking. Sorry, banking. So when banking, you have the angles like that, like so. So in terms of y, so this is basically a slope. So if you can't see it, it's a slope. So here it's Fn. In terms of y, Fn is equal to Fg cosine theta. And we already did a lot of these examples using interval when we did forces and stuff. So cosine theta. And in terms of x, it's going to be Fc, the centripetal force. And then it's going to be mv squared over r. And then it's going to be mg sine theta. And then cancel v squared over r, g sine theta. And that's basically it. Okay, now we move on to the Newton's law of gravitation. So this is our first formula. F is equal to gmm over r squared. So basically m is the greater mass. The lowercase one is the lower mass. So if this is the sun, this is the earth. And if this is the earth, then this is either the moon or a satellite. So it depends. And this is also a constant. So if we go to the table of constants, it's the second one. So for this, we said that F is equal to mg. G is equal to F over M. We just rearrange this formula. Okay, and then we substitute F here. So gm m over r squared. M and M cancel. So it's just going to be gm over r squared. And that's basically everything you need to know. Okay, now we also have the orbital motion, or yeah, so we have orbital velocity. The orbital velocity we can find. I'm going to change this color to back to blue. So the orbital motion, mv squared over r, g, cancel, 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 cancel. Sorry, we cancel this. So v squared is equal to g m over r square root. That's equal to v. And then we also have the another orbital that we're going to take in chapter 10. So keep this in mind. Okay, so next we come to chapter 7, which is nuclear physics. So basically nuclear physics, it's much like chapter 3, which is thermal physics, largely based on concepts. In fact, we're gonna skip this whole part because it's basically based on concepts and the graph and etc. So maybe hopefully in the next upload we can take a look at this. So here, this is the ionization energy. H is Planck's constant. Whenever we say the word constant, we go here, and that's Planck's constant. Okay. And then times the frequency. We know what the frequency is. Um, and then we might ask how we got this formula. Okay, remember that C is equal to F, sorry, lambda F. F is equal to C over lambda. And then we just substituted the energy formula. H C F switch F E H C E. This is basically it. Okay, and now we have this formula. It's pretty easy. If you can remember, this is Einstein's formula. E is equal to mc squared. So what is delta M? Delta M is the mass defect, total mass of the reactants minus the total mass of the product. And there's actually a formula for this. So this is another simple symbol for mass defect. So MP, okay, plus A minus Z. A minus Z will give you the number of neutrons. M nucleus. So this is a nucleus, sorry, for the handwriting. X, here we have A, and then here we have Z. So this is protons and nucleons, nucleus, and then here we have only the protons. And C squared is basically equal to 931.5. It's also constant, so I believe it is here. If I'm not mistaken. Here we are. That's it. The unifying the atomic mass unit. And so, as I said previously, this is mostly theoretical. So hopefully in the next upload. Okay, here we have the energy sources. This is the last topic for SL. So after this, I'm going to start with the HL topic. So bear with me. We have a little bit left to go. So it's basically 8, 9, 10. That's all we have left. So the first thing we have is the specific energy. Specific energy is equal to Q over M. And the energy density is equal to Q over V. So we need to know these formulas by heart. Or you can just, monetize it. So you know that, for example, the formula that we took in thermal chemistry, thermal physics, that Q is equal to MC delta T. So you could make this, and the specific heat was C. So you can make this mnemonic basically. And D's density is always divided by V. So it could work that way. And power is equal to energy over time. And we're going to derive this formula right now. So this formula is in terms of wind power. But before we do that, there is another formula in terms of hydroelectric power. So basically, the power they use and that they use in dams. P is equal to mH over delta T, energy, mgh, potential energy basically. And then this will equal to PVGH, because Sorry, this is raw. So this is the density, because mass is equal to the density times volume. So, and then this will produce P, Q, GH. So Q is basically equal to the energy times that. So Q okay, now we're gonna derive this formula for wind power. So for wind power, K is equal to half V squared. So basically how you find it is gonna apply a similar concept, and we're also gonna consider the coil. It's gonna rotate A, velocity. This is the distance. This is velocity over time because they're, and so the mass is going to be the density over volume. And then if we multiply PV the by this and the area and this volume, we should get this, and we also multiply by half because of the area under the graph in terms of power. Okay, and now we move on to thermal energy. So we know that P is equal to W over delta T. Delta Q over delta T. So the change in thermal heat, or we're talking about thermal energy here. And this will produce K is a conductivity constant over A. And of course, this depends on the material over T over L. So this is cold, this is hot. This is Q, this is L. And this is the area, surface area of that. So, and that's basically how you solve that. Okay, and now we have the black body radiation formula. This is a given formula. And we also have wind displacement law. So this is also pretty given. So this is the maximum wavelength. And then this is a constant over time. And then we also have I's equal to power, the intensity equal to power over the area. I think we took this before. And so now I'm going to be explaining how we're going to use the, or derive basically the solar constant. So I is equal to power over the area, power 4 pi d squared. So the distance between the sun and the earth, it's 1.5 times 10 power of 11. And if we place this in terms with nt, and the power of the sun is 3.9 times 10 to the power of 26. And so if we multiply that by that, we should get around 140 watts meters. -2. This is the solar constant. Okay, and then also, since there is a disk around the Earth that reflects some of the power that and this power obviously affects the intensity. So this is Earth. The actual power that reaches here is different. So 4 pi r squared is the circumference. Or no, sorry, it's the surface area of the planet. So basically, we just substitute the power, and that should give you the power that reaches Earth. One minus this is albedo. So albedo is basically the ratio between the scattered power and the incident power. Scattered power is the stuff that gets reflected, and this is the stuff that is incident. So you want it the other way around. So it's 1 minus that. R square. Pi r squared. And in the end, the power that reaches Earth is going to the power. This is in terms of this is the power that reaches the Earth. So first we calculate this, and then we substitute it in AI. And I just explained the albedo. So albedo basically means white in Latin. So here the intensity is SA. The area is pi r squared. So that gives you the formula. Okay, this is the SL content. And now we're going to move on to the HL content. We have 2 chapters left. So for the first equation, what we're going to do is, so before we actually look at the first equation, we're gonna, actually the first equation we've encountered it before. In the previous, basically the previous, I think it was chapter 6. So I'm gonna move on to discuss the second equation. A is equal to v squared over r, we all know that. And then basically deriving this, we basically substitute value for w. And we said previously what was w equal to in terms of v. I believe it was subtopic 4. So w squared over r. And we also put a negative sign because it is an the triactive force. Actually, the fun fact is that we actually don't derive it this way. We derive it using calculus. So just gonna outline it. I'm gonna really do the whole derivation. So wait, actually, no, never mind. This is how you derive it. I got mistaken with the with another formula. So this is how you derive it. We just put a negative sign because it's basically an attractive force. So Sorry for that. Okay, so then the next formula, we actually derive it from dA is equal to dx, the second derivative of x over dt. And then we bring this to the other side. So basically what you have to do now is to solve this using calculus, and this should produce two formulas. One of them is this, and then the other one is this. So basically, sorry, not that. So you solve this using calculus, and then you get two formulas. One of them is this, and one of them is this. So basically, the one with this sign is going to be your minimum. So a good mnemonic here is min sign, so the last two letters. And then the other one will be obviously the maximum, which is cosine. And also remember in our previous examples when we always assume that in small angles of sine theta equals theta. So basically here we're assuming the same concept. So and then if we wanted to basically differentiate this, we should get this answer. So sine becomes cosine, and the w comes on the outside, and basically we have we do the same here, and so this is still for the minimum. We just differentiated this equation to get to d. This is the dx over dt for both of them, as a matter of fact. Okay, now we are going to derive these two formulas. Okay, so starting off with the one in the bottom, we say that, let me write it here. Okay, so we say that the summation of f is equal to ma. Okay, so this is basically Newton's second law. Then ma is equal to minus kx. Then a is equal to minus kx over m. So this is x. And then a is equal to minus omega squared x cancel the minus signs, we cancel the x's, and then w's are going to be equal to k over m. W is equal to 2 pi over t. And then t is going to be equal to 2 pi m over k, which is this one, the mass spring. So this is basically where we put kx, which is basically the formula for the force, Hooke's law, basically. And now we do the same thing for the pendulum. I'm going to just write it here. Summation forces is equal to minus mg sine theta. Now the reason why we chose sine is because the direction that the so when you have the slope, you have this is going to be cosine, and then this one is going to be the sine component. So MA is equal to minus MG sine theta. M and M cancels, and we're left with A again. So A is equal to negative W squared X, which is equal to minus G sine theta. Sine. Okay, so here we're going to have an angle. So basically L is the length of the rope itself. And then X is going to be the amplitude or the displacement. So it's going to be sine X over L. And then we also said that we apply this concept, and at small angles, this will be minus G X over L. So X and X cancels, and the negative signs cancel. Omega squared is equal to GL. And then just the same thing, the 2 pi over T is equal to G square root of GL. And then finally T is equal to 2 pi L over G. So these are basically given, you don't really have to memorize them. However, it's vital, of course, to know how to derive it. Okay, so moving on, we're going to move on to this equation. Derive it. So we know that EK is equal to M squared. So basically, we're going to substitute this formula. It's a given formula. We don't really necessarily need to know how to derive that. So X not sine. I actually made this one, so. Yeah, so basically, we just derive this. Basically, X naught squared sine squared theta omega t. And then we're going to take sine 90. So this becomes 1. And it's going to be half omega squared x squared. So this is basically our final answer, or the final formula. Now we're going to do the same thing with the E total. E total is equal to, this is the kinetic energy. So the reason why this is the formula is because sine 90. So when this is the maximum, this is supposed to be 90, sorry. This is supposed to be 90. And this is actually the kinetic energy at the maximum point. So the kinetic energy at the maximum point will produce the E total, which is this formula. Okay, so that's that. And now all we need to do is derive this exact formula. So now we're done with this, sorry. To derive this one, we say that E potential is equal to half m omega squared x naught minus half omega squared x naught sine squared wt. So basically we take this as a common factor. Okay, so from our trigonometric identities, this is going to be equal to cosine squared wt and this is going to be equal to so before this we have to just substitute one more thing. So v squared, we're just going to calculate v squared is equal to omega squared. So we're just substituting this for v squared w omega squared, sorry, omega x naught squared sine squared wt. So sorry, this is a long derivation process. Okay, so basically, now that we have this, we just basically wrote this as cosine squared wt and then of course when we simplify this we will get x because x is the basically the distance. So sorry, without the so basically v, I'm going to explain this in a moment. V is equal to w plus or minus w squared x naught squared minus squared. Basically here we took the common factor Before that, we rewrote it in terms of this. And cosine square root of WT. This should give us basically W X. So this is basically sine squared theta. 1 minus cosine squared WT, or sorry, sine squared WT. And as we said previously, we're going to make that 90, and that will be just 1. So it's basically 1 minus 1, and we just simplify that, and then we get this. So basically, we can also substitute it in here instead of cosine, and that's supposed to be what we get. So we just calculate. Yeah, so that's it. And now I'm just going to be explaining this very quickly. So you have two slits. You have this angle. This is going to be a 90-degree triangle. Half sine theta is equal to lambda over 2. Lambda and lambda cancels. Sine. Sorry, this is B. So lambda cancels. This is B, this is lambda sine. This is going to be okay, and then that will be equal to lambda. And you just rearrange this equation. Divided by 2 to cancel the 2's. Equal to lambda. Divide both sides by B. And that will be our final answer. And usually, so I forgot to mention this. Usually, the angle theta has to be less than 10. Okay, and this moves us on to interference. We just draw the two slits and the angle. The first and second slits, and point P. This is also theta. This is also theta. So basically now, when we derive this, or we're going to just basically use the same concept if you remember that we used here in chapter 6. Chapter 4, I believe, yeah, chapter 4 is not mine. So chapter 4 here we used this to derive this formula. So d sine theta is equal to n lambda. Okay, but however, in this part that we also have an equation that's not given, so we say sine theta theta. Of course, this is all at small angles, and then basically these cos n is equal to d sine theta s and d over n. So you should keep this in handy. Okay, now we're going to discuss constructive and destructive interference. So here we are talking about thin film. So we have an incident line, we have the normal, we have a reflected light. So we know that reflected is the same angle on the opposite side of the normal, and we have point A, and then this is refracted, B, C. So I'm not going to discuss the concept, I'm just going to discuss the formula. So basically, this is constructive interference, and this is the formula for destructive interference. However, these two can basically switch if we are looking at the observer side. These two will definitely switch, and if we're looking at the opposite side, it's going to be these equations as they are. Wait, never mind. So basically, constructive interference. So this is basically from the observer side. So these two are from the observer side. However, if you want to look at it from the opposite side, you're gonna switch these. Sorry, you're gonna switch it if you're looking at it from the opposite side. Or if there's one phase change, you might as well switch it. Or if there are two phase changes, then you look at the previous one. You look at it basically like this. So this is the formula for the constructive, and then the other one is the one for the destructive interference. And then also we have to know this equation, the wavelength in the oil is equal to the wave length over the refractive index. Okay, this brings us on to the concept of resolution. So theta over d, of course, this is in rad. Slit separation of the distance of the slits. I can draw it here. However, for the for theta d, it's gonna be 1.22 pi over b. This is all the formula for the circular slits. And for A, it's going to be larger than the one for D. SD can be greater than or equal to 1.22, depending on the slit. So this is basically for the diffraction grading. That's why D. Okay, and then we also have the resolvance or the resolving power. This is also a concept in diffraction grading. So I is equal to the average over the change in delta. Okay, the change is delta sorry, delta. The change in forgot the symbol. The change in the wavelength, in lambda. So it's basically the absolute value of the first wave, the first lambda minus the second lambda. And then the average value. The first plus the second over 2. R is also equal to n times m. And in this case, m is going to be equal to the number of slits. And m is going to be the order. And what do we mean by order is, so is it the first constructive, the second constructive, third, the fourth, etc. Okay. And then this moves us on to the last topic, which is the Doppler effect. So the Doppler effect is when you have something that is either moving or stationary, and then it experiences a change in frequency or pitch. So the higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. We first consider a moving source. This is the formula that we're going to use. And basically what this formula entails is basically that the source has moved this much. And this is the whole velocity. So this is going to be v minus us. And here we have minus. So minus is if it's going towards, so minus is towards. And positive is away from. And when we have a moving observer, it's the other way around. So the negative is away, and the positive is towards. And so basically the way we derive this formula is by saying that lambda is equal to 4 over f and then f is equal to p over that. And then we end up with this equation. Similar concept for the second one as well. However, now we need to discuss the electromagnetic spectrum. So in the electromagnetic spectrum, what is basically the electromagnetic spectrum was when we deal with light. So here we're for the Doppler effect, we're basically dealing with sound. Here it's with light. So this is basically formula for that. And we notice that v is going to be way less than c because c is the speed of light. And we basically derive this formula from c and lambda. And that's basically subtopic 9.5 for the HL students. Now if we move on to topic 10, describing waves. So for describing waves, I'm just going to explain the formulas because deriving them will take a long time. So here we have work. This is the charge. And this is basically the electric potential or the delta E. So you can try to derive this yourself. However, it will take a long time. So here this work is equal to m, the mass, times the gravitational potential. Same concept. And also here we have the formula for the gravitational potential, is equal to minus gm over r, as well as here. And these formulas are easy to derive, however it will take a long time. So I suggest you take a good look at these bunch of questions. So here's the f of d. We already defined all of these variables. However, now I want to derive the escape velocity. So first of all, we say f of c is equal to g mv squared over r is equal to g m over r squared. The square gets cancelled, the m gets cancelled, and we're left with v squared is equal to gm over r. And then now all we have to do is basically, so this is the orbital velocity. So we take the square root of both sides. V is gm over r. Yeah, so this is the orbital velocity. Now to derive the escape velocity, we have to take into consideration the electric and the potential and the kinetic energy. We equate those. G is equal to half v squared. Cancel, cancel. V squared, v squared. Gm over r, and that's basically the escape velocity. Now, the reason why we took the potential energy and the kinetic energy formulas into consideration because we're dealing with the with basically gravity and potential energy at the same time. And there we have it. This was a review, a conclusive review of everything from chapter 1 through 10. Now we still have the chapter 11 and 12. I won't be going in through any options because the options for our year is canceled due to the COVID-19 pandemic that's going on. And basically, during times like these, you have to adapt. So in the same way that I adapt to my my studying techniques, I also have to start to. So basically, we still have to encounter some of these. So basically, most of these formulas are in chapter 7. Anyways, I'm gonna try to cover these in later videos. Have a nice day. Please don't forget to like, share, and subscribe, and hit the notification bell to be alerted when we have our next upload. Our next upload will most likely be about graphs. Other than that, peace out.